Gate exam questions with solution in power system part 5. Question number 21. A 50 MVA, 10 kV, 50 Hz star connected unloaded 3-phase alternator has a synchronous reactance of 1 per unit and a subtransient reactance of 0.2 per unit. If a 3-phase short circuit occurs close to the generator terminals, the ratio of initial and final values of the sinusoidal component of the short circuit current is asked in this question. So we need to find the ratio of initial and final value of sinusoidal component of the short circuit current. So we can relate this short circuit current with the synchronous reactance at the initial stage, and at the final stage short circuit current ISC relate with the subtransient reactance. So these two values are directly given in the problem. So synchronous reactance is 1 and subtransient reactance is 0.2. So 1 by 0.2 is 5. So the correct answer is 5. Next question, question number 22. A single line diagram of a balanced power system is shown in a figure. So the voltage magnitude at the generator internal bus is constant and the value is 1 per unit. The per unit reactance of different components in the system are shown in the figure. The infinite bus voltage magnitude is 1.0. A 3-phase fault occurs at the middle of the line 2. The ratio of maximum real power that can be transferred during the pre-fault condition to the maximum real power that can be transferred under fault condition is asked in the question. So we need to find the ratio of Pmax during pre-fault and Pmax during the faulted condition. Pmax pre-fault by Pmax fault condition. Solution. So draw the pre-fault reactance diagram from the single line diagram given. The reactances are specified in the diagram. The generator reactance is 0.2 and the transformer 1 reactance is 0.1, line 1 reactance 0.5, transformer 2 reactance 0.1 and line 2 reactance is 0.5. So now we can simplify this reactance diagram. These two are in series, so it becomes 0.6, and also these two are in series, it becomes 0.6. So now this parallel combination of 0.6 and 0.6 become 0.3. Now we can add these two, we'll be getting 0.5. And now these two are in series, so 0.3 plus 0.2, it is 0.5. So the equivalent reactance is 0.5, x equivalent equal to 0.5 per unit. Now the maximum real power that can be transferred during the pre-fault condition, that can be given as P max equal to E into V divided by equivalent reactance. So E is voltage magnitude at the generator internal bus, and that is constant and it is given as 1 per unit in the question. And this V is the infinite bus voltage magnitude and it is given as 1 per unit in the question. So you can substitute that 2 here, and x equivalent we found it as 0.5 per unit. Substitute, will be getting 2. So P max is 2 during the pre-fault condition. Now during fault condition, and in the question it is specified, assume the fault at the midpoint of the line 2. Here this is a generator reactance and this is the transformer and line 1 reactance, and here the transformer reactance is 0.1 and the line reactance, overall line reactance at line 2 is 0.5, and the fault occurs at midpoint. So we can divide that line reactance 0.5 by 2, it becomes 0.25 here and 0.5 this side. So the total line at the center point, the fault occurs. So it becomes 0.35 here. So this is a reactance diagram during the fault condition. Now we can simplify this. So this is of a delta format, 0.6, 0.35 and 0.25. Now we are going to convert this delta into star. So at B point, your reactance value will be equal to 0.6 into 0.35 divided by sum of all the 3 reactances. Okay, so that gives you 0.175. Similarly, at C point, 0.6 into 0.25 divided by sum of all 3 reactances. So it becomes 0.125. Similarly, at this point, 0.35 into 0.25 divided by sum of all these 3 reactances, that gives you 0.0729. So the delta is converted into star. Now this 0.2, the reactance at the generator and this reactance are in series, simply you can add. So you'll be getting the complete diagram here. Okay, it looks like star. Now we can convert this star into delta to find the line reactance at the line AC. So converting star to delta, you'll be getting a delta format like this. You need to find this XAC. So considering this star values, and we are going to apply the star to delta conversion formula. XAC equal to the line reactance XA into XC plus XC into XB plus XB into XA whole divided by this XB. Okay, so we are calculating XAC. So in the denominator, this XB comes 0.0729. So applying directly the star conversion formula. So you'll be getting 1.143. This is XAC. Now the maximum real power that can be transferred during the fault condition, EV divided by XAC, and EV, as you know, it is 1 per unit divided by 1.143, that gives you 0.8748. So this is the maximum real power during fault condition. Previously we determined the maximum real power during the pre-fault condition, that is 2. So now we can find the ratio, pre-fault condition divided by during fault condition. So pre-fault condition, the maximum power is 2 divided by the fault condition 0.8748, that gives you 2.286. So the correct answer is 2.286. Now we move on to the next problem. Question number 23. So two identical unloaded generators are connected in parallel as shown in this diagram. Both the generators are having positive, negative and zero sequence impedances of J0.4 per unit, J0.3 per unit and J0.15 per unit respectively. If the pre-fault voltage is 1 per unit, for the line to ground fault at the terminals of the generator, the fault current in per unit is asked in this problem. So direct question, fault current is asked, but the thing is two generators are connected in parallel. Solution. So given the positive, negative and zero sequence impedances and the pre-fault voltage is given as 1 per unit. So for a single line to ground fault or LG fault, the fault current expression can be given as 3EA divided by Z0 plus Z1 plus Z2. So where this EA is your pre-fault voltage. So now two generators are connected in parallel. So the positive sequence impedances Z1 equal to the parallel combination of the given value 0.4 into 0.4 divided by 0.4 plus 0.4, that gives you 0.2 per unit. Similarly for negative sequence impedances Z2 equal to 0.3 parallel combination, you will be getting 0.15 per unit. Zero sequence impedance Z0 is given as Z as synchronous impedance plus 3 into the neutral impedance. Synchronous impedance is given as 0.15 and the neutral impedance is not specified in the problem, so it is 0. So zero sequence impedance is 0.15 and the pre-fault voltage EA is 1 per unit. So direct substitution in the formula. So 3 into 1 divided by 0 sequence is 0.15, positive sequence is 0.2 and negative sequence is 0.15, that gives you 6 per unit. So the correct answer is 6 per unit. Next question, question number 24. The positive, negative and zero sequence reactances of Y connected, that means star connected synchronous generator, are 0.2 per unit, 0.2 per unit and 0.1 per unit respectively. That is positive sequence is 0.2, negative sequence is 0.2 and zero sequence is 0.1. So the generator is open circuit with the terminal voltage of 1 per unit. So open circuit terminal voltage is given as 1 per unit. So the minimum value of inductive reactance in per unit required to be connected between neutral and ground so that the fault current does not exceed 3.75 per unit if the single line to ground fault occurs at the terminal. Assume the fault impedance to be 0. The fault impedance is assumed to be 0 and the sequence impedances are given. Open circuit voltage is specified. We need to find the reactance which is connected between neutral and ground. Solution. So these are the given data and fault current is also specified as 3.75 per unit. So for LG fault again, single line to ground fault, the expression is IF equal to 3EA divided by Z0 plus Z1 plus Z2. So these are the given data, Z1, Z2 and Z0, Zs plus 3 into Zn. So Zs is 0.1 plus 3 into Zn. So this Zn is what we are going to find. So IF equal to 3EA divided by Z0 plus Z1 plus Z2, and we know this IF value 3.75. 3 into EA is generator terminal voltage 1.0, and this Z0 is 0.1 plus 3 Zn plus Z1 is 0.2, Z2 is 0.2. So the only unknown is Zn. So from this we can simplify. Here it is 0.2 plus 0.2 plus 0.1 become 0.5. Take this to this side, multiply and simplify this. Multiply inside the bracket, you will be getting this expression. So Zn equal to 3 minus 1.875 divided by 11.25. That gives you 0.1 per unit. So the correct answer is 0.1 per unit. So this is the reactance required to be connected between the neutral and ground. Question number 25. A 30 MVA 3-phase 50 Hz 13.8 kV star connected synchronous generator has positive, negative and zero sequence reactance 15%, 15% and 5% respectively. A reactance Xn is connected between the neutral of the generator and ground. A double line to ground fault takes place involving phases B and C with the fault impedance of J.1 per unit. So the value of Xn in per unit that will limit the positive sequence generator current to 4270 ampere is asked in this problem. So here also we are going to find the Xn value, or we call in terms of impedance it is Zn value. So the positive sequence generator current is given in amps, that is 4270. Solution: given the positive sequence reactance, negative sequence reactance, zero sequence reactance and fault impedance, then positive sequence generator current. So these are the given data. So the positive sequence generator current is given as 4270 ampere. So it is given in amps. So it is a actual value of current. We need to find the per unit value of current. So per unit value of current equal to actual value of current divided by base current. So base current can be estimated using the formula MVA base divided by root 3 into kV base. So substituting the value which is given in the problem. So 30 into 10 power 6 divided by root 3 into 13.8 into 10 power 3. You will be getting I base equal to 1255.109 ampere. Now the actual value is 4270 given in the problem. Divide by the base value, it gives you 3.4 per unit. So the positive sequence generated current IA1, that will be equal to EA divided by positive sequence impedance Z1 plus parallel combination of Z2 and this whole factor Z0 plus 3ZF plus 3Zn. IA1 is equal to I per unit, substituting that value and substituting Z1 value and keep all the remaining terms as it is. Now taking this whole term to this side, multiplying it with the 3.4 into 0.15, it becomes 0.51 and this term becomes same. Multiplying it with 3.4, this side equal to 1. So taking this term alone, what happens? 1 minus this 0.51 goes to that side, it becomes 1 minus 0.51 whole divided by 3.4. That gives you 0.144. So Z2 parallel with this 3 term, that equal to 0.144. So the parallel combination is 1 by Z2 plus 1 divided by Z0 plus 3ZF plus 3Zn, that will be equal to 1 divided by 0.144. So 1 by R equivalent equal to 1 by R1 plus 1 by R2 plus 1 by R3. So like that we can substitute. So these values are given in the problem. So we can substitute all the values. Z0 plus 3 into ZF plus 3Zn equal to 1 by 0.144 minus 1 by 0.15. So Z2 is 0.15. Taking this Z2 to this side, it becomes minus 1 by 0.15. Simplifying this, you will be getting 3.6. Now 3Zn, we need to find this Zn value. So 3Zn equal to 3.6 minus this other two terms to that side. Z0 is 0.05 minus 3 into ZF. 3 into ZF is 0.1. So substituting, you will be getting Zn equal to 1.08 per unit. So in the option, the correct option is the value of Zn lies between 1.05 to 1.15.